So now that we've gotten through the midterm, it's time to turn our attention to the material which will be covered primarily on the final. Remember that the final will be cumulative, with the focus being on the material covered in chapters 6 through 10. And in these chapters we will be discussing autonomic pharmacology. Now, the autonomic nervous system, like any nervous system, is going to achieve its signaling or its mission through the interaction of neurons with each other. And as you can see in this slide, there is in the upper portion what would be considered the terminus of the presynaptic axon. If you look below that, you'll see the postsynaptic effector cell that has receptors on it, and the number 4 would be pointing to one of those receptors on postsynaptic effector cell. The physical space between that postsynaptic effector cell and the presynaptic axon terminus is called the synaptic cleft. And so, in this model, the axon terminus does not physically touch the postsynaptic effector cell, but rather there's a space in between. And as you can see by Roman numeral 3, the way that these two nerves communicate is through the release of a vesicle, as you see in number 3. That vesicle will fuse to the axon terminus and release its contents into the cleft. And you can see that in the adjacent arrow with the vesicle fusing and releasing its contents into the cleft. And the contents will then diffuse across the cleft down its concentration gradient and bind to postsynaptic receptors on the effector cell. So that's pretty much the scenario. Presynaptic axon terminus, postsynaptic effector cell, synaptic cleft, release of neurotransmitter, allowing communication. So now if you look at this slide, hopefully what you'll see, if you look at the upper portion, is really the central nervous system and the peripheral nervous system. Now, our discussion of the autonomic nervous system falls under the general category of peripheral nervous system. The peripheral nervous system has a sensing division, the part of the nervous system that brings in information. So the things you see, the things you smell, the things you taste, those are considered the sensory division, sending their messages up back into the CNS. The autonomic nervous system is really part of the motor division of the peripheral nervous system. And as you can see here on the left portion, the autonomic nervous system can be further divided into 2 or maybe even 3 nervous systems. The common demarcations are the sympathetic and the parasympathetic divisions. And our textbook even talks about something called the ENS, or the enteric nervous system. Now recall that the autonomic nervous system is largely an autonomous system. Its activities are generally not under conscious control. And it's going to be concerned with regulating visceral functions. That means the functions of the internal organs. Okay, you don't have to think for your heart to beat, it will beat. You know, you don't have to consciously think, oh, my heart needs to beat now, and it has to beat again, and it has to beat again. You don't think about, okay, my intestines have to contract and relax, contract and relax. Those are signals that are taken care of for you by your autonomic nervous system, which is unlike the other branch of the motor division, the somatic nervous system, where conscious controlled functions occur. So, such as moving your arm. You know, you want to pick up a cup on the table that contains some water in it so that you can have a sip of water. You're consciously controlling that movement through the somatic nervous system. So definitely one big difference between the two, autonomic and somatic, is that in the somatic, the signals get executed through conscious control. You're consciously doing something. You're picking up something. You're deciding to walk somewhere. While the autonomic nervous system is mostly concerned with the viscera and not under conscious control. You don't have to think about your heart beating all day long or when you're sleeping, because your autonomic nervous system does. Now, in the autonomic nervous system, in the ANS, we're always going to be discussing a two-neuron link where there will be a preganglionic axon fiber and a postganglionic effector cell. Okay, so there's a two-neuron link. The ganglia are a center into which these neurons enter and meet. That might be best depicted in the slides that are coming. And so the motor division, remember, of the nervous system can be divided into two subdivisions, the autonomic and the somatic. The autonomic nervous system can be broken down into two further subdivisions, as depicted for you here, known as the sympathetic and the parasympathetic. And some textbooks will actually include a third division called the enteric nervous system, which innervates the gut. So just to define some terms, when we talk about sympathetic nervous system, we often, or I should say in past use, a synonym for the sympathetic nervous system was the thoracolumbar nervous system, while a synonym for the parasympathetic nervous system was the craniosacral nervous system. And really those terms, thoracolumbar and craniosacral, refer to the vertebrae from which nerve fibers emanate, depending on whether they're sympathetic or parasympathetic. And I have later a depiction. And so remember, when it comes to the autonomic nervous system, we're dealing with a two-neuron link. The first will be coming out of the brain or the spinal cord, also known as the central nervous system, and entering into a region called the ganglion. Now, the ganglion is depicted for you here as this yellow circle, right, where the first neurons coming out of the brain or out of the spinal cord. And so that first neuron transfers a signal from the brain to the ganglion, and the challenge is to confer the signal from the ganglion to the effector tissue, which could be smooth muscle, which could be glands, etc. And so a ganglion is a collection of neurons where a lot of message exchange goes on. So the first fiber coming out of the central nervous system, depicted for you here by the red neuron coming out of the CNS. Its cell body is in the CNS, but its axon terminus is in the ganglion, which is close to the CNS, but aside from. And so that axon terminus fuses on in the ganglion, forms a synapse with a postganglionic cell, and that postganglionic neuron extends its fiber to an effector tissue, such as smooth muscle, and there that tissue will be stimulated or inhibited based on the signal that's been transmitted through the ganglion. So remember, the ganglion is actually physically a collection of neurons, and it looks like a sphere that sits either close to the spinal cord or close to the effector. And so that might look like something in this slide. On the left panel, we would depict in two dimensions the brain stem, and the spinal cord, which make up the central nervous system. Coming out of the central nervous system is the first neuron. So you can see in all instances depicted for you here, the first neuron is leaving the central nervous system and it's going somewhere. Where is it going? It's going to something called a ganglion, a collection of connections, if you will. And there will be a signal transmitted across the ganglion such that the postganglionic cell will transmit a signal down its axon to an effector tissue. So going from top to bottom, maybe that effector tissue is cardiac and smooth muscle or glands. Maybe it's a renal vascular smooth muscle. Okay. There's some kind of tissue that's going to be affected by that transmitted signal out of the CNS through the ganglion and to the effector tissue. Now, if you notice, there are about 3 ganglia very close to the spinal cord drawn for you on this slide. And those ganglia are defined as sympathetic ganglia because the definition is based on anatomy. And sympathetic ganglia refers to being located at the side of the brain or the spinal cord, on the side of the brain or the spinal cord. So sympathetic ganglia, anatomically speaking, if you were to do a gross dissection of the CNS, the spinal cord, what you would see is these ganglia located on the side of the spinal cord. And these ganglia on the side of the spinal cord are known as sympathetic, based on their anatomy. And there's something I'd like you to notice here, that in sympathetic ganglia, the first fiber is shorter than the second, right? So if you look at the first example of a sympathetic innervation, the first fiber travels a short distance, while the second travels a longer distance to, for example, the sweat glands. If you look at the second example, the first fiber travels a short distance to the ganglion, and the second fiber travels a longer distance to, for example, cardiac or smooth muscle. When you look at the third example, the first fiber travels a short distance to the ganglion, the second fiber travels a longer distance to the renal vascular smooth muscle. And so anatomically speaking, when we talk about sympathetic ganglia, we're talking about those which are on the side of the spinal cord, and a scenario where the first fiber in the connection is short and the second fiber is long. Let's now look at parasympathetic ganglia, outside the spinal cord, outside being around the spinal cord, farther away from the spinal cord, parasympathetic ganglia. Look at what happens to that first fiber. That first fiber travels a long distance, enters the ganglia, while the second fiber travels a very short distance. Oftentimes, that ganglia might even be in the tissue that's being innervated. So do you see the difference? It's a very stark difference. Parasympathetic ganglia are located close to the target organ, while sympathetic ganglia are located close to the spinal cord. If you look down below, you'll see also an example of innervation of the adrenal medulla. And we worry about the adrenal medulla in the autonomic nervous system because it is going to synthesize epinephrine and norepinephrine. The adrenal medulla is often referred to as a modified sympathetic ganglion. Modified sympathetic ganglion. And here's the reason why it's called modified. In the adrenal medulla, you have that first innervation being close to the spinal cord. It's the adrenal gland. So the first fiber is short, and there is no second fiber. In fact, that's why we call it modified sympathetic ganglion. There is no second fiber. Rather, what happens there is stimulation of the adrenal medulla coming out of the CNS causes the immediate release of epinephrine and norepinephrine. Okay, so it's considered modified sympathetic because there's no second fiber really. Okay, but it is sympathetic because it's closer to the spinal cord and because it releases sympathetic stimulants such as epinephrine and norepinephrine. Now, that's a discussion of the anatomy. Where's the ganglia? You should feel comfortable knowing if it's close to the spinal cord or if it's close to the effector tissue. But I'd like you to look at now the connections that occur, because there's really two synapses that we need to consider. The first in the ganglia, the second in the effector organ. Let's consider the first synapse in either type of innervation, whether it's parasympathetic or sympathetic. The first synapse is going to use acetylcholine to confer its signal so that the second fiber can be stimulated and confer its signal to the effector tissue. So I'd like you to take note that in every ganglion that's depicted for you on this slide, the neurotransmitter that's released from the axon terminus of the first neuron in the link is acetylcholine. And the receptor that's present on the postganglionic cell, right, that receptor, which is on the surface of the cell which will extend its axon into an effector tissue, is the nicotinic acetylcholine receptor. Do you remember what kind of receptor that was? Was that a G protein coupled receptor? No. Right? It was a ligand-gated ion channel. So whether that, the ganglion that we're talking about is sympathetic or parasympathetic, the first part of the story reveals the release of acetylcholine and the binding to nicotinic receptor, which then stimulates that postganglionic cell to release an axon into the effector tissue, and the effector tissue gets stimulated upon release of a chemical there. So if we now turn our attention over to the effector tissue, we can see that for example, in the upper example with parasympathetic innervation, the molecule that gets released is also acetylcholine, but now it's binding to muscarinic receptors on the surface of the effector cell. Do you see the difference? The first step of the journey, acetylcholine was released and bound to nicotinic receptors. In the second part of the journey, acetylcholine is released and binds to muscarinic receptors. Do you remember what kind of receptors muscarinic receptors are? G-protein coupled receptors. Right? So in the parasympathetic innervation model, we have acetylcholine at both sites. In the ganglion, we're dealing with activation of the nicotinic receptor. In the effector tissue, we're dealing with activation of the muscarinic receptor. Now let's look to the next example. The first innervation is always acetylcholine and stimulation of the nicotinic receptor in the ganglion. But sympathetic stimulants in the second leg of the journey can come in different forms. So for example, in this second diagram from the top, we see the sympathetic innervation of sweat glands involving release of acetylcholine and stimulation of muscarinic receptor. But isn't that what just happened above in parasympathetic stimulation? Yeah, but muscarinic receptors, when activated in the sweat glands, cause the sweat glands to contract and release their sweat. Right? It's going to make you sweat. It's going to make you sweat by releasing acetylcholine through activation of muscarinic receptor. That's considered sympathetic innervation. If you look below and you look at innervation of cardiac and smooth muscle, what is norepinephrine doing there? Right, that's the second molecule that's released, and it's binding to either alpha or beta receptors. What's happening in the renal vascular smooth muscle? Well, we can see release of dopamine, binding to dopamine receptors. So listen very carefully. Whereas parasympathetic stimulation of effector tissue occurs through muscarinic receptors and acetylcholine stimulating them, sympathetic pathways can involve several neurochemicals in that second step. It can involve acetylcholine and muscarinic receptors if it's sweat glands. It can involve alpha and beta receptors and norepinephrine if it's cardiac or smooth muscle or other types of glands. It can involve dopamine receptors if we're dealing with renal vascular smooth muscle. Now remember, we talked about the adrenal medulla as a modified sympathetic ganglion. And if we look at the second chemical that gets released, remember there is no second fiber or anything. It's different. That's why we call it modified ganglion. But if you look at the chemicals released, it's epinephrine and norepinephrine. Right? And they're going to be able to go to cardiac muscle, smooth muscle, glands. They're going to be able to have their effects through binding to alpha and beta receptors. And last but not least, the type of innervation shown for the somatic innervation is direct stimulation out of the CNS onto the skeletal muscle. And that is the situation when we're dealing with voluntary motor control, right? Wanting to move your arm or raise your hand or stand up to walk out of the room. So definitely look at this information, both here and in your textbook, and feel comfortable with what is the parasympathetic ganglion, what is the sympathetic ganglion. What is the anatomy of this? Where are the ganglia located? Which fiber is shorter? Which fiber is longer? Then, what are the chemicals involved? Well, in all of the ganglia, we see acetylcholine and nicotinic receptor, but in the effector tissues, it depends. If it's parasympathetic, we see acetylcholine and muscarinic receptors. If it's sympathetic, it depends. Usually we think of norepinephrine or epinephrine and alpha and beta receptors, but we can also see activation of sweat glands by acetylcholine through muscarinic receptors. We can see activation of renal vascular smooth muscle through dopamine receptors, and particularly their increased perfusion or vasodilation through activation of those dopamine receptors in the kidney. So this is the first place to start. It's going to then be important to know where are all the receptors in the ANS and what is the consequence of their activation, and that's the hard part. That's a lot more work and a lot more. So just to kind of summarize, In the upper portion, we'd be looking at sympathetic innervations. The first axon coming out of the CNS into the ganglion releases acetylcholine, which binds to nicotinic receptors on the postganglionic cell. That postganglionic cell releases an axon into the effector tissue and will release norepinephrine to stimulate the effector tissue in most instances, unless it's a sweat gland or unless it's the renal vasculature. Right below that, we see acetylcholine being released into the adrenal medulla, which binds directly to nicotinic receptor there, which causes the cells in the medulla to release epinephrine, norepinephrine into the blood, and those hormones travel, or neurotransmitters travel, to target tissue and stimulate alpha or beta receptors in those target tissues. While parasympathetic innervation, that first fiber is longer, the ganglion is located closer to the effector tissue. The first chemical is acetylcholine and the first receptor is nicotinic, but the second chemical is acetylcholine and the second receptor is muscarinic. So which is which? If you look on this slide, we have like a lightish brown area called the CNS, and we have that preganglionic neuron coming out of the CNS into a ganglion, depicted for you here as a yellow circle. Right? On the left panel, the first fiber is short, right, and it releases acetylcholine, which binds to nicotinic receptors. The second fiber is longer, and it goes to its target organ, or it has a modified effect, a modified sympathetic ganglion, which releases its products, epinephrine, norepinephrine, into the blood. Right, that should now be sounding familiar as sympathetic innervation. While on the right side, the CNS, the first neuron coming out of the CNS goes into a ganglion, but that ganglion happens to be either at or very close to the target tissue. In both situations, acetylcholine is released. In the ganglion, the receptor that's stimulated is nicotinic. In the target tissue, the receptor that's stimulated is muscarinic. And there are the answers revealed. Left side would depict sympathetic ganglion. Right side would depict parasympathetic ganglion. Now, I mentioned a little earlier, some textbooks will name the enteric nervous system as the third division of the autonomic nervous system. And this is really a highly specialized nervous system that innervates the gut. It's located in the wall of the GI tract. This nervous system not only receives both parasympathetic and sympathetic innervation, but there's also other transmitters involved that fall into this innervating mechanism. And so you'll see things in the enteric nervous system that are not classical in terms of acetylcholine only or norepinephrine only. You'll see other peptide transmitters that can have effects there, such as VIP, also known as vasoactive intestinal peptides, or substance P, or serotonin. And so that's depicted for you here. If you look at the upper portion of the slide, above now the gut, that would be the lumen of the stomach. Actually, no. I'm incorrect. The lumen will be down by those up and down curves, okay, at the very bottom of the portion of the gut. That would depict for you the surface area. And the outermost layer would be the longitudinal muscle, which is going to participate in contraction or relaxing. And what I'd like you to notice is that the gut, first of all, has two muscle layers. It has a longitudinal muscle layer and it has a circular muscle layer. It has another layer called the myenteric plexus, another layer called the submucosal complex. And as you look through, you'll see both sympathetic and parasympathetic ganglion coming in to the gut. So if you follow any of those sympathetic fibers in, what you'll see is release of norepinephrine. If you follow any of those parasympathetic fibers in, you'll see release of acetylcholine. But if you look around, you'll also see other transmitters there, such as 5-HT, which is serotonin, or NP, which is neuropeptide Y, or SP, which is substance P, Right? Vasoactive intestinal peptide could work in here. And so the reason why some textbooks classify this separately is because there are other transmitters here that are playing a role in the function of the gut, in its contractility, in its relaxation, things such as serotonin, substance P, etc. Those are not classically considered as sympathetic stimulants or parasympathetic stimulants, and so the book classifies them into this third category. Now, the ENS will not be a major focus of what we discuss. These other transmitters. We're going to focus most of our discussion on the classical sympathetic stimulants such as norepinephrine and epinephrine, the classical parasympathetic stimulant of acetylcholine, and drugs that work like those agents. But you should be aware that there are other types of innervation going on in the gut that are contributing to its function. And so, when we look at the neurotransmitters and the receptors in the autonomic nervous system, we have those which can be considered adrenergic and noradrenergic. And these are the receptors that will bind to epinephrine and norepinephrine. These receptors are categorized as alpha or beta receptors, and they are G-protein coupled receptors. Both of the catecholamines, epinephrine, norepinephrine, can activate these types of receptors, but there's a lot of pharmacology there in terms of which of the receptors are mostly activated, which of the receptors have highest affinity for these catecholamines, and other relevant issues we'll discuss, in the days that come. On the other hand, there are cholinergic pathways in the ANS which utilize acetylcholine, and as we've already discussed, acetylcholine, one agent, can affect these two different types of receptors in the ANS, muscarinic or nicotinic. Remember that the muscarinic, there'll be several subtypes, are G-protein coupled, while the nicotinic, which there are two subtypes, are ligand-gated channels. And there's a lot of pharmacology there to discuss about the receptor. So now if you look at the organization of the parasympathetic nervous system, you might remember a few slides ago I mentioned that certain textbooks will call this the craniosacral system, the craniosacral nervous system. And the reason for this designation is if you look at the slide and that first fiber coming out of the CNS, most of those fibers are coming out of either cranial regions or sacral regions of the spinal column. And that first fiber is traveling some distance to a ganglion, which then travels a shorter distance to an effector tissue. And if you look around the wheel here, there's lots of effector tissues for parasympathetic nervous system. The salivary glands, for example, the heart, the lungs, the internal viscera in the abdominal region, such as the liver or the stomach or the pancreas, the reproductive organs, the kidney. So the effect of parasympathetic innervation is going to have, global effects. It's going to do things to different body tissues. And so if you give a drug to a patient that does something to this pathway, either activates it or blocks it, you might get several pharmacologic effects just based on the anatomy and physiology of the innervation. And so it's going to be important to know, what kinds of receptors, parasympathetic receptors are, for example, in the heart or in the lung or in the liver or in the stomach. Okay, so the challenge here is to start to know where are the receptors and how are they innervated. What is the stimulant? What is their ligand? And so I encourage students at this point to consult Chapter 6 and look at that table of ANS innervation. It talks about parasympathetic innervation, the different tissue sites, the different receptors, because that will be things you'll need to know to prepare you well for what's coming. So note that in the parasympathetic nervous system, the ganglion is generally at or near the effector organ, but there are some exceptions. Okay, lacrimal glands and eye, but for the most part, parasympathetic, anatomically speaking, The first fiber is long, travels a long distance to a site very close to or within the effector tissue where the ganglion is, and that second fiber will be short and will release its signal to the effector cell. Okay, so just another way to look at the parasympathetic nervous system, remembering that the first fiber travels out of the CNS some distance to a ganglion which is at or in the effector tissue. The first transmitter release is acetylcholine in the ganglion that binds to acetylcholine nicotinic receptor on the postganglionic effector cell. The second chemical that's released is acetylcholine that binds to muscarinic receptor in the effector tissue. Okay, so just a reminder of the many different sites within the body that are innervated. Now, in the cholinergic synapse, we have the release of acetylcholine that binds to the cholineceptor. Let's first talk about that cholineceptor. If that cholineceptor is found in the ganglion, what kind of cholineceptor is it? It's the nicotinic receptor. If that cholineceptor is found in the effector tissue, which cholinereceptor is it? The muscarinic receptor. So the term cholineceptor, as we now know, is just a general term for a receptor that binds to acetylcholine. You do need to know more about, what kind of acetylcholine receptor is it. If, if you're trying to figure out where are you, if you're in the ganglia or if you're in the effector tissue. So cholineceptor is a general term for a receptor that binds to acetylcholine. And then we know, of course, there are the specific types, the muscarinic or the nicotinic. If that cholineceptor is in the ganglion, it's nicotinic. If that cholinereceptor is in the effector tissue, it's muscarinic. If that cholinereceptor is in the somatic nervous system, it's nicotinic. And so the cholineceptor is going to be able to be stimulated by acetylcholine. And the acetylcholine, where does that come from? It comes from the presynaptic axon terminus. In fact, this slide is trying to show you that choline gets brought into the axon terminus and converted into acetylcholine, ACH, and packaged into a vesicle through the action of an enzyme called CHAT, or choline acetyltransferase. And that may be best illustrated for you in the next slide, where we have choline, the molecule depicted with the quaternary nitrogen, becoming acetylcholine through the action of choline acetyltransferase. Now, if you look at the structure of choline and you look at the structure of acetylcholine, all you really see different is an acetate group being put onto the hydroxy of choline. Do you see that? You see the hydroxy of choline above, and then an acetate group being transferred to the choline to form acetylcholine. So choline acetyltransferase, also known as CHAT, choline acetyltransferase, combines choline with acetate. Where does the acetate come from? It comes from the mitochondria through the production of something called acetyl coenzyme A. So that acetyl coenzyme A is used here as an acetate donor. And the enzyme choline acetyltransferase will take that acetate group and acetylate the choline to form acetylcholine, which is depicted for you as the lower structure. And now if you look at it, you might say to yourself, wow, that's a positively charged structure. That's got a quaternary nitrogen, a full charge. What do you think about that drug in terms of absorption? Not too good, right? You can't just give that drug orally because it will be very poorly absorbed. What about the acetate bond? If you see it, C double bond O, O, CH2, right? That's called an ester link. So what kind of enzyme is going to cleave that to inactivate acetylcholine? It's going to be called an esterase. Can you think of an esterase we already talked about? Right, phase 2 metabolizing enzyme non-specific esterase. Right? So there are plasma esterases that can cleave it, so it won't be very long acting if you give it even into the blood. But nature uses a very special enzyme for the degradation of acetylcholine. It's called acetylcholine esterase. Acetylcholine esterase. But here we're not talking about degradation, really. We're talking about synthesis. And you need chat, and you need choline, and you need acetylcoenzyme A. And so now, if you look at the cholinergic synapse, well, you know what? Maybe we're going to just start the lecture here, because it's a little complicated to do without the pointer. So I think I'll leave you with that. And when we start our next lecture, which will be Friday for my Wednesday-Friday section, or Monday for the Monday-Thursday section, we're going to start at this point. Okay, so make sure that you go through this information. Make sure that you do the blog. Make sure that you're looking at Table 6-1, because all of this is going to help you understand the drugs that are coming in Chapters 7, 8, 9, and 10.